All right, this video here follows directly after a video in which we talked about how we use undetermined coefficients to solve this differential equation right here, where I've got the input force of t squared. We talked a little bit about how to decide what xp we guess with. What I mean by guess is this blue line. What do we start with for the xp to derive and plug in and then figure out our coefficients? Well, the process was derive until the thing either goes away or until it goes away, goes to 0, or until it repeats itself. So we're going to do a couple more. Let's see, right here. All right, same left-hand side, x double prime minus 3x prime plus 2x, but equals t to the fifth. What do you think we would do for that? Pause for a moment, see if you can write down what your undetermined coefficients should be. If you did it correctly, you go all the way out to an f. Here it is. I go at to the fifth, blah, 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 all of these, fifth, fourth, third, squared, t, and no t. So in this case, I go until it goes away, right? So there's a lot of terms there. So let's look at the next example. What if instead of t to the fifth, I had a sine of 5t? I said until you derive it until it goes away, which sine's never going to do, or until it repeats itself. We don't care about the coefficient out front. What we're going to do is we're going to take a sine of 5t plus b cosine of 5t. That's because if I derive sine of 5t, I get a 5 cosine of 5t. And then if I derive that, I come back to something else, a negative 25, sine of 5t, but it has this same base function, and that negative 25 would be a coefficient. So when I have sines and cosines, I go until they either repeat or until they repeat themselves. So oftentimes, at least in these cases, I only have two undetermined coefficients that I'm working with, instead of the previous one where we had 3. I want to show you one that gives us a problem. Zoom out a little bit. 1 over t. Think about this. I want to derive until we go away or until something repeats itself. But 1 over t is t to the negative 1. If I just continually apply power rule to t to the negative 1, we're going to have crazy coefficients out front, but it's never going to derive back to 0 or go away. So what I want you to see is that there are some functions, 1 over t, for which this method is not going to work. Fortunately, many of the functions that we actually care about in applications are ones for which we can actually come up with a undetermined coefficients guess. So let's do one together here. X double prime plus 3x prime plus 2x, so notice this is a plus now, not a minus, equals 10 sine of t. So this one could actually be modeling a spring, a mass of 1, a damper coefficient of 3, and a k value of 2. And what I'm going to do is apply this oscillating function to it. Imagine a force being applied that goes back and forth, and back and forth, and back and forth. The common example of something like this, one thing that we know that oscillates typically is temperature throughout the day. If you look at the weather temperature graph, it often looks a little bit like a sine graph. So say we had something that was not actually a spring, but that acted like a spring. We could apply something like this to it that would make it go up and down. Or say I had like an earthquake and it was pushing back and forth on a building or something like that. Anyway, let's talk about solving this problem. All right, so I need to find my xc first. To find the xc, we do characteristic equations. I get c1 e to the negative t plus c2 e to the negative 2t. You should be pretty good with that. Now, here, I need to choose the xp. I am looking at this function, and I'm saying to myself, what would this derive to, and what functions would I get if I derive it? And I just can't keep counting all the functions until it either repeats itself or it goes away. Well, this one's simple. There's only 2 of them, sine and cosine. Sine derives to sine. sine derives to cosine, cosine derives to negative sine, and then it just starts repeating itself with different numbers out front. So the xp that I take is a sine t plus b cosine t. Derive that, a cosine minus b sine. Derive that again. I get a sine with a negative minus b cosine. From there, I'm going to plug the blue in for the blue, the green in for the single derivative, green, the yellow in there. So when I do that, let's see, what do I have here? All right, so I must have run out of colors with my highlighters, but this right here, negative a sine t minus b cosine t, these colors do not correspond with the colors over there. This right here is this piece right here with that plugged into it. Then I've got 3 times this. That's this right here. So I get 3a cosine t minus 3b sine t. This right here is this multiplied by 3. And the last term is 2a sine plus 2b cosine. That's this plugged into this, so it's doubled, multiplied by 2. And then it's equal to 10 times sine t. So what I want you to see is that I then recolor-coded things. So let's come over here like this. So I need to figure out what a's and b's give me this out. Now, this is one for which I think that doing a system and using REF is very, very nice. So the color coding here, notice I got blue and blue and blue. Those are all the sine terms, and blue on the right side. And I got yellow and yellow and yellow, and those are all the cosine terms. So I build out 2 separate equations because I have 2 unknowns, a and b, and I need to solve them. A sine t plus 3b sine t plus 2a sine t equals 10 sine t. That's all these blue terms packed together. Notice, what do we have? I have 2a sine t and a negative a sine t. So that is nothing more than positive a sine t. What I can do is divide this line by sine of t, which is legitimate, and then get the relationship that a minus 3b is going to be 10. And then that becomes one of the pieces of what I'm going to REF. Then, notice these yellows right here are all of the yellows up there. And again, I've got a b cosine, negative b cosine, and a positive 2b cosine. That gives me this b right here. And this 3a is this 3a right here. And notice on the right-hand side, I don't have a cosine term over here. So what I do is I write it as 0 times cosine. And then I can just divide this whole line by cosine, and I get 3a plus b is 0. And that goes into the REF as well. From there, I plug that into my calculator. Here it is right here. I'll show that to you in my calculator. There's my calculator. 1, negative 310, 310. Quit. Second matrix. Which one is it? B. So I'm going to go math, REF, and then I'm going to go back into the matrix, and I'm going to take matrix B, and I get 1 comma negative 3. So that tells me that A is 1 and B is negative 3. That's what I have written right here. From there, that goes into this right here. My original guess at XP was that XP was A times sine t plus B times cosine t. I then went and plugged that all through this differential equation, used some little math tricks to solve that A is 1 and B is negative 3. So since I've gotten to that point, I can let A be 1, so I get a 1 here, and B be negative 3, so that goes right here. So that gives me my XP equal to sine t plus 3 cosine t. Remember, the whole point here is to get a solution to this differential equation that has 2 c's, and that flows through this equation and gives me 10 sine t. So the 2 solutions piece is the xc. I got to take xc, c1e to the negative t plus c2e to the negative 2t, and add it to this xp that I guessed my way into finding. So I hope that helps you make sense of some of the decision-making process for how to find your xp, and that you feel like you're prepared to be able to go on and solve these types of problems with different XPs, with different forces being applied on the right-hand side. Derive, when does it repeat itself? When does it go away? Take all of the functions you get until one of those two happens. All right, see ya. Bye, thanks.